Yeah, it's the process, the journey. Yeah. But anyway, it's 2:38. Let's get to mathing because we got a lot to do today. Because today we're talking about induction, the thing we started talking about last time. We're already all set up right here. And so let's recall. Well, first let's write down we're talking about induction. Uh-oh, that's going to be precarious. I'll rewrite that later. Specifically, we're on 5.2 today because we're talking about something called weak induction. Oh, you can't see that. We're talking about something called weak induction. And yes, like weak induction compared to what? Strong induction? Yes, there's a weak induction and a strong induction. And the weak induction's weaker, the strong induction's stronger. Math makes sense sometimes, people. So anyway, last time, if you guys recall, we were talking about dominoes. And I spent a long time talking about how to prove dominoes. And we're talking about how to prove a line of dominoes falls over. And by a line of dominoes falling over, I mean that every domino in the line falls over, which is like really pedantic, but you're 10 discrete math, so get used to it. So the interesting thing is, you don't need to know anything about any global behavior. And global behavior, that's one of those words that makes sense if you've taken a lot of math, like I have, but maybe not if you haven't. There's like two, like global and local are like the two things here. Global behavior is behavior about everything as a whole. And so, for example, we have some global knowledge about the even numbers, and that is all even numbers are divisible by 2 or something like that, right? Or like if you took like the average global temperature, or you took the number of people on the earth, right? That's all global behavior. Literally globe in that case is everything, but it just means like everything in a set. Whereas local behavior, it's only things you know about each individual. So that's kind of more interesting. But anyway, so to prove dominoes fall, unlike kind of direct proofs, you don't need to know anything about global behavior. You don't need to know how all of these dominoes interact with each other, right? Because the whole point of dominoes, the whole thing we love about it is it's like a Rube Goldberg machine. It's like a chain, like those giant machines where it's like this domino falls and hits that little robot, which freaking like does that little walk over there and then pops a balloon, and that balloon is like holding something out. Like that's a chain reaction, right? And in order to prove the chain reaction here goes off and they all fall, you don't need to prove anything about all of them at once. All you need to prove is each little individual link in the chain. You just need to prove that this domino will knock over this one, which will knock over this one, which will knock over this one, knock over this one, this one, this one, on and on and on like that. So what I'll say is, you just need to know the following. So to prove that they're all falling, you know two things. One, I'll leave that blank for a second. We're going to come back to that already. But two, the second thing you need to know is that if the nth domino falls, then the n plus 1th domino will fall. So that is the links in your chain, right? So if we call this like the first domino D1, this is D2, D3, D4, D5, D6, D7, D8, and only one of these dominoes sells tacos that'll ruin your dorm room, and that is D2. But anyway, you definitely, to prove all these dominoes fall, you definitely need to know that the nth domino falls and the n plus 1 domino will fall. Definitely need to know that. What's something else you need to know? I mean, for example, if I just stand here and look at these dominoes, will they ever fall if I don't do anything?
Oh, you need to know that the nth domino will fall, no?
You just need to know that one of them will fall.
One of them will fall, yeah.
Exactly. So if you know the nth domino falls, you know the n plus 1 domino will fall, right? But if we did that for every n, it would be like a method of exhaustion thing. We have to check all 1, 2, 3, 4, 5. It would be very exhausting. It would take forever.
Right.
You just need to know one. You need to know that the first domino will fall. And I left that one blank because a lot of people forget this, but it's incredibly, incredibly important right here. So this, you need like your base case, what this will be called later, and then you need this step right here. So the base case connects, just starts it all off, starts off the chain reaction, and then this tells you the chain reaction will work in perpetuity. That's a word, in perpetuity. Yes, legal. Anyway, yeah. So you should know the first domino falls, and you know that the nth domino falls, then the nth plus 1 domino will fall. And then from that, you can conclude that every domino will fall. And why can we do that? Well, we can do that. This all kind of comes back to like our very first lecture of class. We're talking about, like I got really abstract. I was talking about there's like this is like the truth. Like if the truth is here, then you can link it to this statement, which links to that statement, links to that statement. Well, let's call the nth domino falling, right? Let's call that P of n. And it's called the n plus 1 domino falling, P of n plus 1. All I'm saying here is that P of n is defined as the nth domino falls. So P of n is a predicate, right? It's a statement that takes in a variable. We can think of it as a property, right? If P of n is true, that means n has the property that the nth domino falls. There's a certain way to think about that. So the point is we can rewrite number 2 here. This is the same thing as saying P of n implies P of n plus 1. Oh, you guys can see that. That's in the weird glare spot. This right here, the blue we could rewrite as for all n greater than or equal to 1, P of n implies P of n plus 1, and the first domino falls, that's the same thing as P of n. And by the way, it's important, right? It's very important that you know, it's very important that this right here is the same. I accidentally used UVA colors. Oh my God. Very important that this right here is the same thing as this right here. And what I mean by that is this is your connection. But we'll get to that in a second. So anyway, so the point is if you know that P of 1 is true, the first domino falls, and you know that P of n implies P of n plus 1 for all n greater than or equal to 1, well then you can make this chain right here, where you basically have P of 1 implies P of 2, which implies P of 3, which implies P of 4, which implies P of 5, which implies P of 6, on and on and on and on like that. And you can go from 1 to 2, you know that's true by the second fact. That's true by 2, that's true by 2, that's true by 2, that's true by 2, that's true by 2. You can do that. But like Tor said, we have to connect this to the truth somewhere, right? This is just a bunch of logical connections. This statement's connected to this, connected to this, connected to this, connected to this, connected to this. But how do we know any of them are true? We're just connecting the truth of them, but we don't know any are true. We have to connect at least one to the truth. And so we can connect P of 1 to like the truth by 1. And now, once we connect P of 1 to the truth, which is by our fact 1 that the first domino will fall, because I'm going to push it over, then that connects the rest. And so we have this giant logical chain here, meaning everything in the chain is true. To show that P of 6 is true, well, you know P of 1 is true by 1. That tells you P of 2, P of 3, P of 4, P of 5, P of 6. But you can do that for any n, right? It doesn't matter what it is. It doesn't have to be 6. And so what I was talking about before is the very important one very important thing to keep in mind is that this right here, your base case, has to connect up with where this chain reaction starts taking over. In the sense that these dominoes are good because we know that for all n greater than 1, if P of n falls, then P of n plus 1 will fall. Meaning 1 will imply 2 falls, 2 implies 3 falls, stuff like that. But what if you had a gap? Like if this was only true for all n greater than or equal to 2, right? That would be saying that it's only like if the second domino falls, then the third will fall, and the fourth, fifth, sixth, all on. But it doesn't say that the first domino falls, the second will fall. So there could be this gap here, right? And that would like get rid of this connection right here. Without that connection, you can't connect the rest of this chain to the truth. Right? Nothing happens. So the point is, you need to make sure that this chain really is all connected and that the base case, this guy, connects to the chain reaction and all works. But anyway, the point is, if you know the first domino will fall, and you know for all n greater than or equal to 1, P of n implies P of n plus 1, then every single domino in the chain should fall. Does math work? Let's find out. Yes. Right? This is all that induction is. This is all that induction is saying. And right now it feels like we're just talking about dominoes, but now it's connected to everything else. Any questions about anything we just did here? Good, I hope this is making sense.